Today we're going to talk about reactions in which gases can be formed. But we're going to start out with a couple of quizkins. So, as usual, stop the video, try the quizkin. I'll give you answers in a minute. Well, here we're looking at the reaction between aqueous lead 2 acetate, so that'd be PbC2H3O2, and aqueous sodium iodide. So that'd be NaI, and that's AQ, aqueous. Here are our products. Well, lead and iodine don't make a soluble compound. So there's our precipitate, and it's PbI2, so that's solid, plus, and now I have sodium together with acetate. Well, that would be soluble, because most acetates are soluble, and all group 1s are soluble. Now, if I'm going to balance this, I'd need a 2 here to balance my acetate. That means I need a 2 here to balance my sodium, and that would also balance my iodine. So there's the molecular equation. Oh, sodium acetate is aqueous. Now, if I want the ionic equation, I can split up the aqueous things. I can split up the things that are electrolytes. So Pb2 plus is separate from C2H3O2 1-, and there are 2 of these. Also, sodium and iodine can be split up. So 2 Na pluses and 2 I minuses. PbI2 I can't split up because that's a precipitate, but sodium acetate I can. So 2 Na pluses and 2 C2H3O2 minuses. To do the net ionic equation, I have to figure out what my spectators are, and they turn out to be acetate and sodium. So my net ionic equation is Pb2 plus 2 I minus makes PbI2. Give this one a try, and I'll give you an answer in a moment. In this reaction, aqueous ammonium chloride, which is NH4Cl, is reacting with aqueous silver nitrate, which is AgNO3. Here's our products. Silver chloride is not soluble, so I have a precipitate of AgCl. So I put solid there. But ammonium nitrate would be soluble. Ammonium salts are soluble, and nitrate salts are all soluble, so that's an AQ. It's already balanced. As an ionic reaction, I'll split up all the electrolytes. So NH4 plus Cl minus plus Ag plus NO3 1-. Those are both aqueous and soluble. AgCl I can't split up because it's a solid, and ammonium nitrate I can. So NH4 plus NO3 minus. To make my net ionic equation, I look for my spectators, which are nitrate and ammonium, and that gives me this net ionic reaction. Cl minus plus Ag plus makes AgCl. Another quizkin. Here you're looking for molecular ionic and net ionic equations for the reaction between sodium hydroxide and acetic acid. Stop the video, try it yourself. I'll give you the answer in a minute. So here we've got aqueous sodium hydroxide reacting with aqueous acetic acid. So that's HC2H3O2. That's a molecule. That's not an ionic compound. It says aqueous. What are our products? Well, this is an acid-base reaction. So I'm going to get water, and I'm going to get a salt. And the salt is the cation from the base, that'd be sodium, together with the anion from the acid, which would be acetate. Sodium's 1+, acetate's 1-, so it's NaC2H3O2. And group 1 salts are all soluble. Most acetate salts are also soluble, so AQ goes after that one. It's balanced right now. Ionic equation. Sodium hydroxide I can split up. Na plus and OH minus. Acetic acid I can't because it's not one of our 6 strong acids. I have to keep it together. Since it's not a strong electrolyte, mostly it's not in solution as ions. It's mostly still molecules. Water, it's a molecule, not a strong electrolyte. Sodium acetate I can split up because that's a soluble salt. So Na plus C2H3O2 1-. To do the net ionic equation, I have to take the spectators out, and there's only one. It's sodium. So the result is OH minus plus HC2H3O2 makes water, and C2H3O2 1 minus. Well, just like metathesis or double replacement reactions can produce precipitates that don't dissolve in water, they can also produce gases that sometimes don't dissolve in water. And when these gases are produced, they come out of the solution in the form of bubbles. So these are visible reactions that produce gases. There are 4 classes of reactions that we're going to study that produce gases. 3 of them are reactions of acids with something, and 1 of them is a reaction of bases with something. First of all, anytime you have a salt that has as its anion carbonate or bicarbonate, when that reacts with an acid, you're going to get a particular class of reactions. First of all, let's identify, just a reminder, what carbonate is. Carbonate is CO3 2-, and bicarbonate is HCO3 with a 1- charge. When either of those is the anion in a reactant and the other reactant is an acid, you will get a particular kind of reaction that ends up producing a gas. This is the sequence that it happens in. First thing that happens is carbonic acid and a salt get formed. Like, let's say we were doing this reaction, HCl reacting with NaHCO3. If you took the normal pattern of double replacement reactions and take the inside 2 species and the outside 2 species and put them together, you'd end up with these products. NaCl, that's the salt that gets produced, and then you'd get H2CO3. Well, that's carbonic acid, that H2CO3. Carbonic acid, however, isn't very stable, and so the carbonic acid decomposes. So you get a secondary reaction that takes place immediately where this breaks down to give you H2O and CO2, carbon dioxide, which is a gas. So the H2CO3 is really an intermediate species, and it doesn't really exist, not for very long. Ultimately, you just pass straight over and produce these 3 products. So the consistent products of a carbonate or bicarbonate with an acid is CO2 gas, H2O, water, liquid water, and then a salt. And that salt is always going to be the anion from the acid with the cation from the carbonate or bicarbonate. So overall, the reaction that we were just looking at, we would write as HCl plus NaHCO3 reacting to form NaCl aqueous plus water plus CO2 gas. Now, if we were going to write an ionic equation, we could split up the HCl into H plus and Cl minus because it's a strong acid. Sodium bicarbonate is a sodium salt. They're always soluble because sodium is a group 1. So that's Na plus and HCO3 minus. Sodium chloride you can split up because that's a strong electrolyte. Water you can't. And also CO2 you can't. Net ionic reaction? Well, sodium ions and chloride ions are both spectators here. So the overall reaction is just that H plus reacting with bicarbonate gives you water and carbon dioxide. So this means any carbonate or any bicarbonate with any acid will give these products, and that CO2 gas is the gas that's formed in this reaction. Let's take a look at another one. Even if you have an insoluble carbonate, like calcium carbonate doesn't dissolve in water, it will dissolve in an acid. For example, if I dissolve this with hydrochloric acid, HCl, it doesn't dissolve by dissociation. It dissolves by a gas-forming reaction. This is an acid with a carbonate, so I'm going to get CO2 gas plus H2O plus a salt. And that salt's going to be the cation calcium with the anion chlorine. Calcium chloride, CaCl2. If I were to balance this reaction, I'd have to put a 2 there. So notice that the calcium carbonate dissolves in the acid while it wouldn't have dissolved in water. What's the ionic equation? Well, you still can't split up calcium carbonate. So that has to stay together because it's a solid. H plus and Cl minus come from the strong acid HCl. Carbon dioxide is a molecule that's not an electrolyte, same with water. Calcium chloride is soluble, so that's a Ca2 plus and 2 Cl minuses. And we actually have two H pluses and two Cl minuses on the left-hand side. Forgot about that coefficient. Net ionic reaction. Well, chloride's a spectator here, but it's the only one. So CaCO3 plus 2H plus gives carbon dioxide, water, and calcium ions. That's the net ionic reaction. Another class of gas-forming reactions works in a very similar way to the last one that we saw, and that's sulfites and bisulfites. Sulfite is SO3 2-, and bisulfite is HSO3 1-. When those are the anion, no matter what acid you react it with, you're going to predictably get SO2, H2O, and a salt. And again, here's how it works. The first thing that happens is the double replacement or metathesis reaction produces sulfurous acid. So this is kind of an analogy to carbonic acid. But it, like carbonic acid, isn't stable, and so then it decomposes. But instead of giving CO2 and water, it gives SO2 gas and water. And then there's always a salt, and that's formed in the initial reaction. So the final products are SO2, H2O, and a salt when these reactions happen. Here's an example. Let's say we had Na2SO3, this is sodium sulfite, in aqueous solution, and we reacted it with the strong acid HBr, acids in aqueous solution. Our products are going to predictably be SO2 gas, water, and a salt. That salt comes from the anion from the acid combined with the cation from the sulfite, and that gives us NaBr. NaBr would be aqueous. Sodium salts are all soluble. To balance this, I'd have to put a 2 there in front of the sodium bromide and a 2 in front of the HBr. Ionic reaction. The sodium sulfite would be soluble. HBr is a strong acid, so I can split that up into H plus and Br minus. SO2 is a molecular gas, not an electrolyte. Water, not an electrolyte. Sodium bromide is an electrolyte, so 2 Na pluses and 2 Br minuses. What are my spectators? 2 sodiums, 2 bromines. The net ionic reaction is SO3 2- reacting with 2H plus gives SO2 gas and water. Third gas-forming reaction. This is when sulfides react with acids. Sulfide is just the monatomic anion from the sulfur atom. The products are H2S, which is a gas, and then a salt. Let's take a look at a reaction example. K2S in aqueous solution. If this were reacting with HNO3, nitric acid, a strong acid, we would get, if we combine the inside two species together, H2S, and that's our gas. That's the rotten egg gas, actually. It smells bad. And the outside two species would be the salt. So potassium with nitrate, KNO3. And that would be aqueous because potassium is a group 1. To balance, I'd have to have a 2 here, and then I'd have to have a 2 here. Ionic reaction. Potassium sulfide could be split up. Nitric acid is a strong acid, so that would give 2 H pluses and 2 nitrates. H2S is a molecule that's not a strong electrolyte, and potassium nitrate is a strong electrolyte. Potassium is a spectator. Nitrate is a spectator, and the overall reaction is S2- and 2H plus gives H2S. So that's the heart of this gas-forming reaction because H2S is a gas. Another class of gas-forming reactions is when we react a base with an ammonium salt. Ammonium is NH4+. So when that's the cation and you react it with a base, you will get ammonia gas, water, and a salt. Again, this has got an intermediary step, sort of like the sulfite and carbonate reactions. First thing that happens is NH4OH and a salt form. But NH4OH is really just an acid-base reaction waiting to happen. NH4 plus is a weak acid. OH minus is a strong base. And when these things react with each other, as soon as they're formed, this happens, the strong base OH rips a proton away from the ammonium and leaves it as ammonia, which is a gas. And then, with the extra proton, OH minus becomes a water. So that's where those come from. And then we get a salt from the cation of the base and the anion from the ammonium salt. Here's an example. Here's the base, NaOH, sodium hydroxide. Let's say it reacted with ammonium chloride, NH4Cl, in aqueous solution. First product we know will be NH3 gas. We also know we're going to get water, and we'll get a salt that comes from sodium hydroxide's cation and ammonium chloride's anion. So that would be NaCl, and that's aqueous because group 1 salts are all soluble. The ionic equation would be Na plus OH minus plus NH4 plus Cl minus. NH3 we cannot split up, it's not a strong electrolyte. Same thing for water, but NaCl does get split up to Na pluses and Cl minuses. Chloride is a spectator, sodium is a spectator, and that leaves us this net ionic reaction. OH minus plus NH4 plus is NH3 and water. So the only thing that's really happening in this reaction, unless the salt happens to precipitate out, is that reaction between the products, OH minus and NH4 plus. We are thinking about ammonia as a gas, but in fact, lots of teachers and textbooks don't mention this. Ammonia really dissolves in water really well. It doesn't dissociate, it doesn't ionize, it's not a strong electrolyte, but the molecules do spread out in the water so that they don't form bubbles of gas. So it's perfectly appropriate to write NH3 aqueous as well. In fact, it's probably a little more correct. So we know now about precipitation forming reactions, we know about gas forming reactions, and we know about acid-base reactions. Let's develop a scheme for predicting a metathesis reaction that you might have thrown at you. I would say the first thing that you want to do is ask yourself, are the reactants an acid and a base? If the reactants are an acid and a base, well then you have an acid-base neutralization reaction, and your products are going to be water and a salt. You find the salt by taking the cation from the base and the anion from the acid and just putting them together. Second question you want to ask yourself is, if you had an acid for one of your reactants, but you don't have a base for the other one, then do I have a carbonate in the other reactant or a bicarbonate? If I do, I'm going to get CO2 and H2O and a salt. Those are going to be my products. If I have an acid and I don't have a base, but I do have a sulfite or a bisulfite in my other reactant, then I'll get as products SO2 and H2O and a salt. And if I had an acid and no base, but I had a sulfide for my other reactant, then I'll get H2S gas plus a salt. Now, if one reactant wasn't an acid, there's still another possibility. One of the reactants could have been a base. If one reactant was a base and the other one wasn't an acid, you can check this out. If the other reactant is a salt of ammonium, then you're going to get NH3 gas, or aqueous, and water, and a salt. So now we know how to deal with any case that we are thrown at that has an acid or a base, or an acid and a base. What if you don't have either? If you don't have either an acid or a base, then it's not an acid-base reaction, it's not a gas-forming reaction, and then your next step is to look for precipitate formation. So you ask yourself, based on what you know about solubility, are any of the products insoluble? Are any of them things that you know from your solubility rules not to dissolve in water? If that's the case, then you have a precipitate forming reaction, and the product will be at least one precipitate. Let's apply this to some examples. You give this a try. Pause the video, try and predict the products, and then look back again and see what my answers are and see if they agree with yours. Okay, as I'm asking myself my questions, I recognize I do have an acid. HI is an acid, but I don't have a base over here. So it's not an acid-base neutralization. However, I do have a sulfide. The anion for Na2S is sulfide. When that happens, I know I'm going to have as my products H2S gas and a salt. The salt is just the cation from the sulfide, the Na, together with the anion from the acid, which is I. Na plus, I minus makes NaI. And group 1 salts are all soluble. So, ionic equation. Na plus could be split up from S2 minus. Hi is a strong acid, so that makes it a strong electrolyte. I can split that up. H2S is just a molecule. It's not a strong electrolyte. I can't split that up. But NaI I can. So that's Na plus and I minus. I haven't balanced here. I should go back and do that. To balance this, I'd have to put a 2 in front of NaI, and that would require a 2 in front of Hi. Well, that changes my ionic equation as well. I need a 2 here and here. I'd also need a 2 here and here. Net ionic equation. 2 iodides cancel out. 2 sodiums cancel out. My net ionic equation is S2 minus plus 2H plus gives me H2S. Okay, give this a try. I'll be back with the answer in a second. Okay, HF is an acid. This is not a base, so it's not an acid-base neutralization. So the next thing I want to look for is gas formation. Acids, when they're in the presence of SO3, sulfite, are going to make a gas, and that gas is SO2. In addition, they'll make water and a salt. And the salt here is going to be lithium together with fluoride, LiF. That will be aqueous. SO2 is a gas. The reaction is balanced. If I want an ionic, it's Li plus and HSO3 minus plus. Oh, I have to keep HF together because it's not one of my 6 strong acids, so I have to keep that together as HF. Over here, SO2 can't be split up. H2O is just a molecule. And lithium fluoride can be split up because that would be a soluble salt. So Li plus and F minus. We only have one spectator here, that's lithium. So here's my overall net ionic reaction. HSO3 minus reacts with HF and gives me SO2 and H2O and F minus. Here's another one. Give it a try. Come back for the answer. Well, KOH is a base. NH4NO3 is not an acid, so this is not an acid-base neutralization. However, when I have a base and I have an ammonium salt, which is what this is, I will have a gas-forming reaction that produces ammonia. So NH3 gas or aqueous is one of my products. Second product is water, and then the third product is going to be the salt that's made up from the K from the KOH and the nitrate from the NH4NO3. That will be aqueous. The equation is balanced. Net ionic equation would be NH4 plus NO3 minus. I can split that up. Nitrate salts are all soluble. KOH is a strong electrolyte. NH3 I cannot split up. H2O I cannot split up. And potassium nitrate I definitely can split up. It's a group 1 and it's a nitrate, and they're all soluble. Nitrate's a spectator. Potassium is a spectator. The net ionic reaction is NH4 plus OH minus makes ammonia and water. Give this one a try. Stop the video, work it out, look for my answer. Well, HC2H3O2 is acetic acid. That's an acid. You can spot that because it starts with H. KOH is a base. You can spot that because it ends in OH. So we have a simple acid-base neutralization here. Water and a salt are going to be my products. H2O, and the salt is the K from the base together with the acetate ion from the acid. C2H3O2 is 1 minus, K is 1 plus, and so they balance each other out. That's aqueous because group 1 salts are all soluble. Reaction's balanced. If I'm going to do an ionic equation, I can split up the KOH, but I cannot split up the acetic acid. It is not one of my strong acids, so it's not a strong electrolyte. I shouldn't show it as ions because mostly in solution it isn't. H2O can't be split up, but potassium acetate could as K plus and C2H3O2 1 minus. Potassium ions cancel out. That's it. So the net ionic reaction is OH minus plus acetic acid makes water and C2H3O2 1 minus. Couple more. Give this a try and come back for the answer in a bit. All right, this reaction has got a base here, LiOH. CuSO4 is not an acid. It's also not carbonate, bicarbonate, sulfite, bisulfite, or sulfide. It's sulfate. So this is not a gas-forming reaction. The last thing we've got to check for then is this something that could produce a precipitate? Well, let's look at the combinations. Lithium would go together with sulfate. Lithium's a group 1. They're always soluble, so that's not a precipitate. Copper could go together with hydroxide. Well, hydroxide salts and oxide salts are usually not soluble. The only exceptions are group 1s, calcium, strontium, and barium, and copper isn't one of those exceptions. So we do have a precipitate. The precipitate is CuOH2. This is copper 2 sulfate, so 2 hydroxides go with the copper. So that's a solid, a precipitate. And then the other salt that we have here is lithium sulfate. Sulfate is 2 minus, so it's Li2SO4. That's aqueous. Group 1s are always aqueous. To balance this, I would need a 2 in front of the lithium hydroxide. Ionic equation. I can split up lithium hydroxide to 2 Li's and 2 OH's. Copper 2 sulfate soluble, that's Cu2 plus and SO4 2 minus. Copper hydroxide is not soluble. Hydroxides aren't soluble, so I keep that together as CuOH2. But the lithium sulfate I can split up to 2 lithium ions. I've got some spectators. 2 lithiums on each side don't change. I can take those out. 2 sulfates, 1 on each side, also don't change. So the net ionic reaction here is really 2OH minus and Cu2 plus makes CuOH2. One more. Give this a try and then look for my answer in a minute. Okay, this is sodium nitrate and potassium iodide. Neither one is an acid, neither one's a base. So that means it's not acid-base, and it also means it's not going to be a gas former of any kind. So, does it precipitate form? So let's inspect. Sodium together with iodide? No, sodium would not be a precipitate. It's always soluble. Potassium together with nitrate, also a group 1. So that would always be soluble. So we have no precipitate, no gas formed, and no acid-base neutralization. What is it? Well, this is not a reaction at all. No reaction. Well, now we know about precipitation, acid-base neutralization, and 4 kinds of gas-forming reactions. We're starting to get a pretty good arsenal of equation predicting tools here. We're going to learn about a little bit more in the next video and then start to apply this to something realistic that we can use to solve problems in lab.